This is Jordan Detloff, and I'm presenting over my question, which is describe the physical significance of the constants in the first and second order transfer function. So I'm going to talk a little bit about first and second order transfer functions and then describe the constants that we can see. In a first order transfer function, you see the standard form first order transfer function. I have listed that when you take the Laplace transform, you see the equation that you actually use, which is k over tau s plus 1. In a second order transfer function, I listed the standard form again, but we usually just deal with the Laplace transform. K, which is the value on top, is the gain of the function. It's calculated by dividing the output range by the input range. So obviously the units are output unit over input unit. I have some listed, as such. They're going to change with whatever kind of system you're using. The effects of K graphically, as K increases, your plateau is going to be at a higher level. Not the same slope, but they increase about the same way. They just plateau at a higher value. Tau is your time constant. So obviously the units are time. Seconds, minutes, hours. Seconds, your response time is going to be quick, but hours, it's going to be a little longer before you see a response. Physically, time is approximately 63.2% of your final value. So looking at a graph where this plateau happens. So I have little red tick marks of where your final value is, that plateau. 63.2% roughly, obviously. So you go over to your function and you find that time, which is usually what your x-axis is, and that's your time constant. So I also graphed a second order transfer function to show you, let you have a little comparison value. And here you can see in the where the transfer functions are different. The upper one is your first order transfer function, and the lower one that kind of dips, that is your second order transfer function. So I graphed them so that your plateau is the same value, but obviously our taus are different for the first and second order. Zeta is the thing that's different. It's only in your second transfer function, but I've listed values of zeta. Critically damped, only really going to happen in your homework, not really in industry. So underdamped, oscillatory, overdamped, not oscillatory, but somewhat sluggish. I have listed a graph that is actually in our book on page 143. You can see our critically damped values there in the middle, and as you increase your zeta value, so as I said, it becomes sluggish. Then as you decrease your zeta value, you actually increase your graph, but it also becomes increasingly oscillatory. So as you become closer to 0, it's going to oscillate more. If I were to graph this out, it would oscillate until it finally reached a steady state of 0. If you have any questions, I'm sure Patton will be very ready to answer them. Thank you.